Today, my presentation will deal with the prediction of interfacial debonding between stiff particles and a soft matter. I will propose to use the coupled criterion, which is a finite factor mechanics approach. And I will try to show you how to use it and how you can use it to analyze experimental data. First, I will begin to explain what is the coupled criterion. So please, if something is not clear, do not hesitate to interrupt me and ask directly a question. So let us imagine you have somewhere a solid here and a stress concentrator. For example, here a sharp notch, and you submit the sample here to a tensile loading, and you would like to predict the crack initiation here. Of course, it's not a standard problem because you do not have a crack, but you have here a notch, a stress concentrator, and you cannot use a standard approach of fractal mechanics. What we propose here is to use a finite fractal mechanics approach, which is a coupled criterion, which combines two conditions: stress condition and an energy condition. Okay, so the stress condition simply states that along the anticipated crack path, the opening crack, the normal opening stress along the crack path should be greater than the strength of the material. Okay, this is the stress condition. If you plot the stress condition versus the crack length here, you obtain a decreasing curve, of course. The energy condition states that if you make the difference between the initial elastic energy and the elastic energy and the initial potential energy, sorry, minus the potential energy with a given crack length, then this difference must be greater than the energy necessary to create the crack. Here, of course, Gc is the fracture energy of the solid. You can write this condition like this. You just have to write this difference and you divide by the crack increment, and then you introduce what we call the incremental energy release rate. This is why we call it finite fractal mechanics, but because here you have a finite surface of the crack area, and then it is not the usual Griffith energy release rate, and we call it the incremental energy release rate. Okay, if you plot this incremental energy release rate versus the crack surface, you obtain an increasing energy, an increasing curve. And then you have to combine both conditions to define crack onset. You would like to have the critical loading at crack onset, and you would like to have the crack increment at crack onset. Then, okay, here for the stress condition provides an upper bound, and the energy condition gives a lower bound. And if you increase the loading, you will move the two bounds. And finally, for only one unique loading, you will have only one loading and one value of the crack increment, which is the value at crack onset. Okay. This is a typical standard application of the coupled criterion. I will show in the following slides that combining these two conditions naturally introduce a material length. I will call it LC here, which is the fracture energy divided by the square of the strength. And I will show that this crack length at initiation, crack surface at initiation, depends on this length and on the geometry, of course, geometry of the stress concentrator. And also that the critical loading at crack onset depends on the strength, also on the material length, and also on the geometry. Now, if you consider the simple problem here, this is a defect here, a sharp notch submitted to a tensile load. If you apply the coupled criterion, you will obtain this curve, which plots the critical load at crack onset divided by the strength of the material, and you plot this versus the ratio of the initial size of the flow here divided by the material length. And you obtain this kind of curve, which clearly shows the size effect behavior. Okay, if you have a very small defect compared to the material length, you have no effect on the critical strength, the critical stress. The stress at crack onset is the strength of the material. There is the presence of the defect can be ignored. And on the contrary, if you have a large defect here, you can consider that this flow behaves like a crack, because this is the standard value obtained from an edge crack with linear elastic fracture mechanics here. Okay, so you have a nice transition here between stress-controlled situation and energy situation here with a transition here. You can check this with experimental data. For example, here I use data from Cook with ceramic materials, alumina, titanium barium, titanate barium here. And okay, in the literature you have all the properties of these materials, and you can plot here the data, and you can verify that you have the size effect I showed just before. Okay, in this case, the experimental data are obtained from a bending test performed on samples, and the defects are indentation flow introduced in the ceramics. Okay, I will now switch to another problem. Here you have a composite, a matrix reinforced with particles. And as you know, if you introduce particles in a matrix, stiff particles in a soft matrix, you will improve the properties of the composite. The properties of the composite depends on the properties of the components, but also on the properties of the interface between the particle and the matrix. And it is known that if you want to have good properties, good toughness of the composite, you have to adjust the interfacial properties to induce decohesion here upon tensile loading. Due to the stress concentration at the poles of the particles, the debonding will initiate first at the poles and then propagates along the interface. This was shown in some experiments here. Most of the experiments are made from glass particles in the polymer matrix. And you can see here the debonding zone, the debonded zone. Sometimes also you have a debonding, and then you have crack kinking into the matrix. Okay. These phenomena are well known, and they are usually described with such kind of formulas. So the debonding stress scales with the fractal energy of the interface. Here you have additional term which depends on the residual stress, and the constant here is more or less empirical. Most of the time you have to make a choice for the size of the debonding zone. Okay. So we would like to investigate this problem with a coupled criterion, and I will describe all the procedure. So first, I would like to write something about the stress condition and here the energy condition. So I will introduce the geometry of a particle, the angle which defines the bounded zone here. And what we would like to capture is the critical stress at onset of debonding and the angle which corresponds to the debonding along the interface. Okay, and we are going to apply the coupled criterion, which combines then the stress condition and the energy condition. So first, we have to decide what kind of representative volume element we will deal with. Okay, for simplicity, we assume a perfect distribution. Let's say an hexagonal distribution of the particles, and we replace the hexagon by a cylinder. So we can use axisymmetric limitations. Okay, and so I define the radius of the particle, the radius of the matrix, the particle volume fraction. I also introduce what I call the interfacial modulus, which is a kind of harmonic average of the modulus of the particle and the modulus of the matrix. And I will present some results only for a given ratio of the elastic moduli of the particle and the matrix. Okay. So if we link the energy and the stress and the energy conditions with the applied strain, we can write the stress condition like this and the energy condition like this. Here we introduce a factor which is a kind of stress concentration factor, which depends on the angle, which depends on the geometry. And here we introduce normalized incremental energy release rate, which also depends on the angle and on the geometry. Okay. These factors are evaluated with the help of finite elements calculations. Here I will use an axisymmetric model. Here is only the quarter of the cell is needed because you have symmetry conditions. Of course, here we have to use boundary conditions so that the lateral face of the cylinder remains straight. Okay. So to evaluate the stress concentration factor, it's very simple. You just have to make a computation with the interface bounded. But to compute the incremental energy release rate, you have to simulate the propagation of a crack here. So you have to release the nodes along the interface. You also have to have a mesh fine enough. And okay, so it is necessary to perform a study with increasing refinement of the mesh, and in practice, the discretization of the angle along the interface will be lower than 1 degree. I recommend this paper, recent papers, where we define our practical considerations for using the coupled criterion, either with asymptotic point of view or with a finite element point of view. Okay, so if we compute these coefficients, we obtain the stress condition here, that is to say the stress concentration factor. So you see the stress concentration is not so strong, and it is a decreasing curve. Here you have the energy condition with the incremental energy release rate. The point here is that you have a maximum. It is not a monotonically increasing curve. So it's introduced some something you have to deal with when applying the coupled criterion. So as we have a maximum here for the incremental energy release rate, we can assume that the energy condition is first satisfied at this maximum here. So it is written here, and following the coupled criterion, crack onset will start if the stress condition is also satisfied for this angle. So we write the relevant stress condition, and we have this drives this inequality here, where we naturally introduces a length. I will call it the interfacial length. Here you have the factor energy of the interface, and here you have the strength of the interface. And this length must be compared with, which is material length, interfacial length, must be compared with a structural length, which is beta multiplied by the radius of the particle. Beta is a purely structural parameter. Okay, and if this condition is satisfied, that is to say, if the interfacial length is large enough, then the energy condition is satisfied independently of the stress condition. Okay, so in this case, the mode is the dominant mode, the controlling mode is the energy condition. And then the crack onset, the crack angle will jump automatically to the maximum value here, and the stress at crack onset only depends on the interfacial fracture energy here. If it is not the case, if the interfacial crack length is not large enough, then to determine the angle at crack onset, you have to solve this equation, which shows that the angle, so the crack surface at crack initiation depends on this interfacial length, and you can deduce the critical stress at crack onset, which now depends on the fracture energy and on the interfacial strength. So you have a combined regime. Okay, so finally, for this problem of interfacial debonding, the solution can be written like this, and it is plotted here in terms of debonding stress divided by the interfacial strength versus the interfacial length divided by the radius of the particle. You still have a size effect here. That is to say, if the interfacial length is large enough as compared to the particle radius, you are dominated by the energy condition. The angle at, which is plotted here, the angle at crack initiation is plotted here versus the same parameter here, and the angle is maximum, and it is dominated by the energy. But if you reduce this ratio, that is to say, if you increase the radius of the particle, you enter the mixed mode, I will say. Both energy and stress conditions are dominating, and the angle at quark initiation, at debonding initiation, is smaller. Okay, so what can we do with such kinds of results? We would like to analyze some experimental data. Okay, so what I will recommend in this case is to plot some ISO values in the interfacial fracture energy, interfacial strength plane. Okay, so this green curve for a given debonding stress corresponds to all the couples, all the couples of fracture energy, fracture parameters, which corresponds to this debonding stress. Okay, and you can see that here you have two bounds on the axis. This bound corresponds to a very high value of the interfacial length. This means it is dominated by the energy, and this bound corresponds to the stress condition. It is dominated by the stress condition. Okay. So if you have several experiments with, of course, the same interfacial parameters, you can plot several ISO values, and theoretically, these curves should match in one point, which corresponds to the identified to the good value of the interfacial properties. Okay. So we have done this for several experiments found in the literature. For example, the data of Shaw et al. They made several batches of composites with glass particles and polymer matrix. Here you have the properties, the volume fraction, and the particles, the radius particles are different and induce, of course, different debonding stress. So for each radius, you have to plot such kind of curves. You plot different curves for the different radii here, and you have to adjust to obtain the best choice. And the results are plotted here. And you can see that we obtain, this is the prediction of the coupled criterion. These points correspond to the experimental data. For the interfacial factor properties estimated here, only we have one point which does not match here. This point is for a very small particle, very small particles. In this case, the predicted value is very high, and it is likely that in this case the fracture mechanism is different. It may involve the matrix tracking, because the strength of the matrix is about 50 MPa in this case, and debonding is not the dominant mechanism. Okay. We can also perform, we use some another data, and in this case, it is also glass particle composites. And in this case, we have a strong variation of the particle volume fraction. Only two kinds of particles in terms of radius. Okay, and it's possible. The agreement is not perfect, but in fact, it's quite difficult experimentally to determine the stress at debonding, and this is probably the reason of the less good agreement in this case. Okay, now we will consider a new problem. Sometimes the composites are made at high temperature, and if the thermal expansion coefficient of the particle is larger than the one of the matrix, upon cooling, you will induce some tensile stress at the interface, and this can cause interfacial debonding. So in this case, you have no mechanical loading. So loading is a change in temperature. Okay. So it's very easy to handle the problem. You just have to write the stress condition. Here, the loading is temperature change. So you have a stress concentration factor, which does not depend on the angle, of course, because the loading is hydrostatic. And here you have, for the energy condition, you have a new incremental energy to this rate due to this new kind of solicitation. You solve the problem, exactly the same thing, and you have exactly the same kind of results. And here I got the change of temperature, which is responsible of debonding, versus the ratio of the interfacial length over the radius of the particle. And you still obtain a size effect, here dominated by the stress condition, and here dominated by the energy condition. Okay, this kind of considerations were used to analyze some data, old data from David and Green on ceramic matrix composites elaborated by hot tracing at high temperature, and two batch of data with different radius of different particle radii here, and two batch of interfacial conditions. And there was one radius here, there was no interfacial cracking, and one radius, there was always interfacial cracking. This is very important information. You can use it. You assume that everything seems driven by the radius. So you consider that the energy condition is driving. So you write the energy condition. In this case, no cracking, and in this case, always cracking. And you are able to derive some bounds, in fact, bounds on the fracture energy. And if you say that you are in the energy domain, energy control domain, this condition in terms of interfacial length should be satisfied. And you can derive also some estimation on the interfacial fracture energies, maximum interfacial fracture energy. Okay, so in this case, the identification of the interfacial fracture parameters is not complete, but you are able to derive some bounds. Okay, and now you can also, if you assume that upon cooling there is no cracking, now you can superimpose mechanical loading. That is to say, you analyze the presence, the occurrence of debonding due to a mechanical or tensile loading, but with the presence of interfacial stress, of interfacial residual stress. And so you restart with a coupled criterion. You write the stress condition. So here you have a mechanical term and residual stress term. You do the same thing for the energy condition. This is a little bit more complex because here, in principle, you may have a list another coupling terms, but we have checked. In fact, it is very small, and you can skip it. And so, in fact, the debonding stress in presence of residual stress, you obtain this kind of expression. Here you have kappa. This term is simply the ratio of the residual stress divided by the interfacial stress, and this is this term which is which takes into account the presence of residual stress. And if you plot, you obtain this this kind of curve. Here you have no residual stress, and then you increase the amount of residual stresses. It is clear that if you increase residual stresses at the interface, you decrease the debonding stress, but only for large particles, because for small particles, the mechanical load is always the. Okay, now to show you another possibility with the coupled criterion, you can just wonder, is it possible to take into account the shear stress? Okay, because obviously at the debonding, the normal stress is dominating, but as soon as the angle is increasing here, the shear stress here is more and more present. So the question is it necessary at the onset of debonding to take into account the mode mixity, the mixed mode? Okay. This is very often a question we have. So to do this, one solution is you have to modify the stress condition and you have to modify the energy condition. Not very complicated, but it can be done. So for the stress condition, you can introduce an equivalent stress. In this equivalent stress, you combine the normal stress and you combine the shear stress. Of course, you have to introduce now, here you have the interfacial strength, and here you have the interfacial shear strength. You have a second parameter to take into account, of course. You can do like this, and here you have the equivalent stress concentration factor here. Okay, for the energy condition, what you can do is to introduce the mode mixity, usually defined as the ratio between the shear and the normal stress. And then one solution is to use an empirical law which links the interfacial factor energy to this mode mixity. And this is a phenomenological law introduced by Hutchinson and Suo, and lambda is a parameter you have to fit with experimental data. For example, just look at this nice and recent results from University of Seville here. They had made experimental test with Brazilian test geometry. Here they have an interface, a glued interface, and you can see that the interfacial factor energy is increasing with the mode mix here, and it is easy to fit the parameter lambda to obtain this empirical law. And then you modify the energy condition. Here you have the incremental energy release rate, but now here to estimate the factor energy, you have to integrate this interfacial energy, which now depends on the mixed mode. So it's just an additional term you have to introduce, and the energy condition writes like this here. And so finally, if you look at our, coming back to our debonding problem, here with mu, if you remember, is the ratio of the strengths is here. If you have a high value of mu, you can ignore mode mixity, and a low value of mu, you take into account mixity. Lambda, this is a parameter of signal. So it seems that the mixed mode is important for the angle. It modifies quite a lot the angle. But if you go back to the critical stress, it does not change so much. Okay. So it's something I observe very often in this problem of interfacial debonding. Mixed mode is important for propagation, but not so much for debonding. Okay. So now just to a few words about stability. You would like to know if the crack once initiated is stable or not. Okay, so in this case, it is a simple problem of propagation. So you can use the Griffiths criterion here. Here you have the energy release rate. Here, this is the incremental energy release rate. And of course, you have a relation between those two quantities. It is very simple. The incremental energy release rate, you have to integrate the energy release rate. And so you have a simple relationship between Griffiths energy release rate and the incremental energy release rate. And remember, if you are in the energy mode, if the interfacial length is large enough, that means that the angle is at the maximum and you are at the maximum of J incremental. So the derivative of J incremental is 0. So you have the exact equality between incremental and energy release rate. So if you are in this case, theoretically, the crack is stable. Once initiated, it is stable. This is a crack arrest, it is called in fractal mechanics. Okay. So now, just to go a little bit further, we have seen some data here. It appears that the crack has debonded and then cracks, kinks into the matrix. Okay. So you have exactly this situation. And this is a little bit complicated, in fact, because if you know interfacial crack propagation, you cannot analyze this kind of situation, that is to say, the kink out of an interface with the standard Griffiths criterion, because in this case, you have some oscillations in the solutions, and you cannot define the standard energy release rate for this situation of kink. That is like this. This is the interfacial crack propagation. You can define without any problem the energy release rate for the interfacial crack propagation, but not for the crack kinking out of the interface. Because if you decrease the length of the kink, you will have some oscillation in the solution, and you have no definition of the energy release rate. So one solution, at least theoretical, is to use one more time the coupled criterion, because in this case, we do not have to make the kink very small. We just assume a finite length of the kink, and it will work. So once more time, you apply the coupled criterion. I do not re-explain the situation. I hope that you know now. So we introduce now the matrix length with the parameters of the matrix, the factor energy of the matrix, the matrix strength. We still have a structural parameter, And we obtain exactly the same kind of situation with energy dominated situation, stress energy dominated. And it can be used to analyze this kind of situation. For example, if we assume that both the interfacial crack initiation and the crack kinking is both dominated by the energy condition, it's very comfortable because you can write, for example, this kind of conditions. That is to say, the stress for crack kinking is lower than the stress for debonding, which means that once the crack has debonded, she will be stable here because we are in the energy dominated situation. And if we satisfy also these conditions, the crack will automatically kink into the matrix. So we will have debonding followed by a kink into the matrix. Of course, we can also imagine to simulate different scenarios. I mean, the crack will may not kink directly, but may propagate along the interface. This is very well described by the Griffiths criterion, taking into account the mode mix of the interface. Of course, the interfacial energy is growing as soon as the angle increases, as we have seen, and so the probability of kinking also increases. Okay, I think it's now time to conclude. Just I hope I have shown how to use the couple criterion to deal with this problem of debonding. So I tried to summarize. It's very quick to obtain the solution. In fact, you just have two parameters to estimate the stress concentration factor, only one finite element computation. The energy will illustrate several computations because you have to release nodes, but it's not so complicated. With these two parameters, you have the solution for many interfacial parameters. So if you change the interfacial parameters, like in the cohesive solid models, you do not have to re-perform the computations. Okay. You can estimate experimental data by fitting experimental data. You can take residual stress into account. You can also take interfacial mixed mode. And more generally, it is not a demonstration, but I have explored a quite large range of situations for interfacial debonding or interfacial interactions and so on. And most of the time, we have some kind of results if we plot the critical stress versus the strength, and here in terms of material interfacial length, we have an energy domain, a stress domain, and a transition zone. Okay. And just to conclude, I would like to. It is all the results. Many of the results are in this paper, and I would like to thank my co-authors here. Dominique, Anita from INESEM, and Nicolas from Amsterdam. If you are interested by finite factor mechanics, also, I would like to inform you that there is a European network animated by Professor Mantic from Seville, which is very active in the field of finite factor mechanics and also in the field of phase fields, which compare both data. And within the framework of the ASIS European Structural Integrity Association, there is a technical group animated by Professor Yossi Bash from Tel Aviv on finite chapter mechanics. Okay.
Okay.
Thank you for your